Good morning, students. So today I am going to explain discrete time Fourier transform. I am Dr. Rajlakshmi, Associate Professor, belongs to EC Department and Panniyar Engineering College, Chennai. So the topic what we are going to discuss now is discrete time Fourier transform. See, this is represented as a continuous time signal in time domain. So this axis is y-axis is represented as the amplitude axis, whereas x-axis is represented as the time axis. This is a way to represent a signal. So generally, the continuous time signal is represented as x of t. So when we are going to apply Fourier transform over the continuous time signal, we will get the frequency domain representation as capital X of j omega or capital X of omega or capital X of e power j omega. All the notations are referred as frequency domain transform only. All are same. So Fourier transform helps to convert the spatial domain data into frequency domain data. That means time domain data into frequency domain data. In frequency domain, we have magnitude as well as frequency detail. So uh, we have the data for the particular frequency, what is the magnitude it possesses. That we will get or extract only from the frequency domain. So Fourier transform is a tool which can easily convert time domain details into frequency domain mapping. So to complete one cycle, it takes 2 pi radians. So now we are going to discuss about discrete time Fourier transform. As we discussed, Fourier transform can be applied for continuous time signal as well as discrete time signal. So the Fourier transform for continuous time signal is referred as continuous time Fourier transform. Similarly, the Fourier transform which is going to apply for discrete time signal is referred as discrete time Fourier transform. See, first we'll get the Dft, which is called discrete Fourier transform. From the Dft, we derived Dtft because Dft is not suitable for digital application. In Dft, again, the frequency domain is continuous. So we have to sample the frequency domain data at the interval of 2 pi by n for k samples. So this is how we derived Dtft from Dft. So Dtft is meant for discrete time Fourier transform. So we'll get Dtft by sample the Dft. Hope this point is clear to all. So for all digital applications, we need Dtft. So first, the signal will be in a time domain. So we have to apply Fourier transform. So we will get d of t. So that dft is further going to be sampled at the rate of 2 pi by n. We will get the dtft. So the dtft for dtft. See, this is how we'll get the DTFT. So in DTFT, n is equal to r to the power m. R is nothing but base or radix. M is nothing but the number of computational stages, whereas n is nothing but the n point DFT. So this is the formula for DTFT. So x of k equal to summation n varies from 0 to capital N minus 1 x of n into e power minus j 2 pi by n into kn. So what is the formula for DFT? So the DFT formula is x of k varies from x of k equal to summation n varies from 0 to n minus 1 x of n into e power minus j 2 pi n. So here that DFT is sampled at the rate of n, we will get the discrete time Fourier transform. So this is the formula for discrete time Fourier transform. So once we get the DTFT, the data will be processed and then finally it has to be converted into time domain detail. So The inverse Dtft formula is x of n equal to 1 by n summation k varies from 0 to n minus 1 x of k into e to the power plus j 2 pi by n into kn. So this is for inverse Dtft and this is for Dtft. So what is x of n? X of n is nothing but discrete time signal. So it is a time domain signal. X of k is nothing but frequency domain values. So in frequency transform, we have real part as well as imaginary part. So that is represented as x of k consists of real value as well as imaginary value. So your so at the result of Dtft, we are going to draw two spectra. One is called magnitude spectra, another one is called phase spectra. So for magnitude spectra, first we have to calculate the magnitudes for particular k values. So mod x of k equal to square root of real part square plus imaginary part square. Similarly, for phase angle, the formula which we are going to use is tan inverse of imaginary part of the x of k divided by the real part of the x of k. See one example. I'm going to explain with one example so that you will understand the concept clear. See, the time domain data are given. So x of n is the discrete time domain signal. So here the x of n is defined as 1 for 0 to 2 interval. Then 0 for other values. So sketch the magnitude as well as phase spectra for the given discrete time signal. So this is the discrete time signal. Now we have to write the formula for 4-point Dtft. So x of k equal to summation n varies from 0 to capital N minus 1 x of n into e power minus j 2 pi by capital N into kn. So we are going to compute 4-point Dft. So this capital N value will be 4. So the length of the sequence, actual length of the sequence is 3. Okay. So here the n should be greater than or equal to l. So n equal to 4. So first we have to calculate. The k value. K varies from 0 to 3. So when k equal to 0, that is x of 0, we will get. So n is equal, here this n varies from 0 to 3, 4-point Dft. So here we have only 3 values are given in the problem. So the fourth value is considered as 0. So substitute here, we will get the answers. So capital X of 0, capital X of 1, okay, then capital X of 2 as well as capital X of 3. Capital X of 3, so only 3 values, right? So the fourth value is going to be 0. So this is our Dtft values. X of k equal to 3 comma minus j comma 1 comma plus j. So now we have to get the magnitude spectra. So for sketching the magnitude spectra, we have to calculate the magnitude values. So here again the k varies from 0 to 3 because 4-point Dft. So first we have to calculate 0, k is equal to 0. It is real part square plus imaginary part square. Here 3 is complete real part, so 3. So here there is no, for the second value there is no real part, only imaginary part. Third one is completely real part. So we will get the magnitudes and plot the magnitudes. So for magnitude spectrum is going to drawn between the magnitude versus k. Similarly for phase spectrum, we have to calculate the phase angles. So tan inverse of imaginary part divided by real part. So calculate it, we will get the phase spectra. So angle of x of k versus k. Similarly, for the same problem, we can able to calculate 8-point Dft. So here the n should be 8. So what is the actual length of the signal? 3. So we have to add 5 more zeros, or we have to append 5 more zeros. Then write the formula for Dft. And your k values varies from 0 to 7. Find all your x of k values 0 to 7 and tabulate all our x of k values. Next we have to calculate the magnitude spectra. mod x of k equal to real part square plus imaginary part square. So again we have to calculate magnitude for first 8 samples 0 to 7. Plot all the magnitude values with respect to k value. For when k equal to 0, the magnitude is 3. When k equal to 1, the magnitude will be 2.414. K equal to 2, the magnitude will be 1. Like that, right? We will get the magnitude spectra. So after 8 values, the spectra will be repeated for the next 8 values. Similarly, phase spectrum, calculate the phase angle using the formula. So this is 8-point Dft. So 8 angles should be calculated. Angle points 0 to 7. Phase spectra is always drawn between the phase value versus k. So we have positive phase angle value as well as negative phase angle value. So plot all the values. So this is the phase spectra, phase details. Thank you. Hope you understand the concept clearly. So if you have any doubt, you comment in the query section so that I will answer. Thank you. We'll meet you again.